Hi, I'm Kaylee from Baldwin-Wallace University.
And I'm Mark from Ohio Wesleyan University.
And this summer we studied star spots on a star called LO Pegasi. And a star spot is a cool dark region on the stellar surface. And the physics behind it is really interesting. They form because the stellar gas in the star is ionized to create a conducting plasma. And in a perfect conductor, the resistance would be zero. So according to Ohm's law, the EMF would also be zero. And then applying that to Faraday's law, that would mean that we would have to have a constant magnetic flux. And in this image here, if this loop is a perfect conductor, as it moves towards the right, to maintain that constant flux, the three magnetic field lines that are going through the surface of that loop would have to move with the loop itself, and this is called flux freezing. And in a star, this flux freezing also happens, but instead of having a loop, it's the plasma that the magnetic field lines move with. And in a star spot, the magnetic field is coming straight out, and it has a magnitude, or its magnetic field has a magnitude of a few thousand Gauss, and in comparison, the magnetic field of the Earth is around 0.5 Gauss. So the magnetic field of a star spot is very large. And also the V cross B forces in the star spot restrict side-to-side movement of the gas, so it suppresses convection, and therefore the primary way of energy transportation in the star spot is through radiative diffusion, whereas the primary method is convection everywhere else. And radiative diffusion is a lot less efficient at transporting energy in the star spot, so that's what leads to the cooler, darker appearance that we see. And also, according to the Babcock model, this flux freezing combined with differential rotation, which is when the gas around the equator is moving faster than the gas at the poles of the star. So you can see that the magnetic field lines are flowing, or they're being carried around the star due to its differential rotation, and eventually we get these kinks. So there are these magnetic flux tubes that are below the photosphere that are less dense than their surroundings. So therefore they're buoyant. They want to rise out of the surface. So it's like if you had a pool noodle in water and you tried to push it under the water, it would kink out in the middle. And that's what happens with these flux tubes. And the footprints where the flux tubes are coming out of the photosphere, that's where we see these star spots. And they usually come in pairs of opposite polarity. And then as far as instrumentation goes to actually observe LO Pegasi, which is the star we're interested in, we used a Meade 14-inch LX600 telescope, as well as a quantum scientific imaging model 632 CCD camera, and we used the Astrodon standard photometric filters, which are blue, red, infrared, and visual.
So when we take our telescope and point it at our star, we also take a couple of other images, including dark frames and flat fields, and those are used to process our images in order to help us reduce systematic error and increase our signal-to-noise ratio. So the dark frame, what it does is it helps to eliminate the uncertainties that come from hot pixels and dark current, inherent properties of the CCD chip. And the flat field frame, what it does is it helps to compensate for vignetting, which is when an image is brighter at the center than at the surrounding edges. So after we have our reduced images and they've been processed, we put them into Mira Pro and do what is called differential aperture photometry. And we have SAO 89758 as our comparison star, and GSC 21881044 as our check star. So then what we do once we have our magnitudes calculated for the brightness of our LO Pegasi, we can use a program called Paranzo to calculate the period of rotation for the star. Once we have a period, we can make what's called a phase plot. A phase plot is a plot of magnitude versus rotational phase starting at some arbitrary point in time. And what rotational phase is if you imagine the star spot facing you, this would be 0.25 phase, 0.5 phase, 0.75, and then back to 1, and 1 and 0 are going to be the same. So as we can see here, we have some phase plots through the 4 standard photometric filters. We have B, V, R, and I. And you can see that through our I filter, the amplitude is much lower than the amplitude of the B filter. And that's because the star spot, like Kaylee said, is cooler than the surrounding star. So the contrast through the infrared filter of the brightness of the spot compared to the brightness of the rest of the star, is much lower than the contrast through the B filter, and that's because they act as black bodies, and the amount of radiation that they are emitting is wavelength dependent. So because we get different information from the different 4 filters, we can exploit the fact that limb darkening is going to be different through the 4 filters, and that is what allows us to determine the latitude resolution in our algorithm that was developed by Dr. Harmon called light curve inversion. And what this does is, like I said, exploits the degree of limb darkening through each of the 4 filters in order to resolve the latitude of the spot. So here are some images from 2006 to 2011 of the star spots. And we don't have 2012 and 2013 because what happened in those years was our light curves were of lower brightness and overall lower amplitude, which suggests the existence of a spot on the visible pole of LO Pegasi, because if there were a spot on the pole here, as it rotates, it wouldn't be carried out of view, leading to an overall dimmer light curve. So in order to correct for that, recent work was done by Dr. Harmon to imagine a arbitrary sized pole spot on top of the star, and then to correct, it will calculate what it thinks the spots are, provided that there's a spot on the pole. Now, this isn't perfect, and it was just done recently, so not much work has been done to analyze the 2012-2013 data, that's why it's not included here. But this is very cool because our star is 80 light years away, and we're able to produce an image of its surface based on these light curves.